In this lesson, we're going to examine how we can calculate limits in some faster ways, some more robust ways, if you will, instead of having to do left and right hand limits all the time. We start off by looking at polynomials. So polynomial functions are considered continuous over their entire domain. That is, you can draw them without ever lifting your pencil. So you could draw a quartic, you can draw a quadratic, you can draw just a line at the polynomial. Every single point on that graph exists. And as you approach every point on the graph, if you think about left-hand bound and right-hand bound, if I approach something from the left and I approach something from the right, it's going to come out to that point. In fact, it's going to come out to the point f at a. So we can actually show that as we approach any point on the graph, the limit as you approach the point is actually the point itself for polynomials because they have to exist. They're continuous. So instead of having to do left-hand bounds and right-hand bounds to figure out what's happening as we approach it, we can literally plug the value into the function and say, here's what's going to happen as we approach that point, as long as it's a polynomial. So let's look at an example here. I have myself a polynomial. It's a quadratic. What happens as I approach 1? Well, if I want to, I could try a little bit below 1, a little bit above 1. I can do that. And I can do this, but I know it's actually faster to find f at 1 because I know it's going to exist. I know there's not going to be a hole, there's not going to be an asymptote, there's not going to be a jump. It's a polynomial. It exists. So if we put 1 in for all the x's, and then we calculate, we get 4. As we approach 1, the graph approaches 4. Much faster than doing left and right hand limits, especially when we get to more complicated ones. Look at the second one. Again, it's a polynomial. And just to point out how you know things are polynomials, you have x's to positive whole number exponents. That's what makes this a polynomial, okay? They have to be positive and whole number exponents. Okay, so you couldn't have x to the half, that wouldn't work, or x to the negative 2. Again, I could do the left and right bound if I wanted to, or it's faster to just figure out f at negative 2. So negative 2 to the 4 plus 2 times negative 2 squared. Put in our calculators and we get 24. And if we try the third one, what's happening as I approach 5? Now, in this case, you don't really see an x because it's a linear function with a power of 0 on it, basically. Okay, so what's going to happen as I approach 5? Well, because this line is a line at 2, no matter what I approach, our function is always going to come out to 2. Okay, that's kind of a trick one there. There is no x, so you don't have to worry about what's happening. It's always the same. Okay, so as soon as we recognize polynomials, don't do left and right hand bounds anymore. Or sorry, left and right hand limits. Just plug it into the function. It's going to come out with the same value. But for the ones that that aren't polynomials, we have to figure out how we're going to approach these ones. Some shortcuts for these. So there's 3 different kinds of breaks you could have in your graph. And we've looked at some of them. And we want to figure out by looking at their limits what kind of breaks they have. So option number 1, we have a point discontinuity. In this kind of thing, we're going to get a hole because some factor can be canceled on the top and bottom of a rational function. So for example, a rational function might be, this doesn't necessarily match the graph, okay, but maybe we have x minus 2 on top and x minus 2 and x plus 1 on the bottom. Fix that up a little bit. Do it the other way around. X minus 2 on the top, and x plus 1 on the top, x minus 2 on the bottom. Okay, this would be a rational function, yes, because it's a fraction, but I can cancel this and this, leaving me with a line. Well, because I canceled something, that means there was a hole. And there was a hole specifically at x equals 2, the part that was canceled out. Okay. Now, when I try that with my limit idea, I'm going to figure out there's a pattern that comes with this kind of limit. We'll get to those in a second. The second thing I could have is a jump discontinuity. This is a piecewise function. These are the more obvious looking ones. You can tell it's piecewise because it's made up of pieces. Maybe you have x plus 1 for when x is less than 0. Maybe you have x squared when x is between 0 and, let's say, 1. Maybe it's x cubed when x is greater than 1. They have different pieces, and those pieces may or may not be connected to each other. You can tell by evaluating the endpoints, what's happening at 0 and 1. Do they come out to the same values? Do they come out to different values? Okay. There, you have to do sort of left and right hand limits as you approach the endpoints. Okay, so we won't spend too much time with jump discontinuities. They're kind of obvious ones. The third one is an infinite discontinuity. And by that we mean there's a vertical asymptote. So again, we could tell it's maybe I'm having an asymptote in it if it's a rational function, okay, which means it has a value on the bottom, an x on the bottom, let's say, or an x squared or something like that. And on the top, we've got something else. So as soon as I put an x on the bottom, that cannot be canceled out. So unlike the whole, I can't cancel x with x here. That means I have a vertical discontinuity. Okay, I have an asymptote. There's going to be some sort of break. So these are our three types. Now, we don't want to have to go through and graph them all to actually figure out which kind of discontinuity it has. We want to be able to do this using our limits, because we can see what happens as we approach from the left and as we approach from the right. Oh, there's something going on here. But I also don't want to have to go through left and right hand limits. I want a shortcut for it. So here's our ideas for today. To prove the discontinuity, we're going to have to see what happens at the point. We're going to see the limit as we approach it. For a rational function, which involves things like holes or vertical asymptotes, what you can do to figure out the limit as you approach a point is figure out the limit of the top and figure out the limit of the bottom separately. If it comes out to a number, then hey, that's where that graph approaches, a number. But if it comes out to something over 0, then you've proven there's a vertical asymptote automatically. As soon as you see something over 0, a vertical asymptote. If you try it and you get a value of 0 over 0, we call that indeterminate, and you've proven the presence of a hole in the graph. Okay, so those are our two options basically. We're either going to get, three options. We're either going to get a number, we're going to get something over 0, or we're going to get 0 over 0. For the ones where you get the hole, 0 over 0, the limit still exists. And you can actually calculate, since from the left and the right hand side you're approaching a number. Okay. But to find that limit, to find that value, you have to actually do a little bit of work, because 0 over 0 is not a value to that, right? So to do a little bit of work, we're going to have to try to simplify the function by factoring or by rationalizing first. We're going to make the function easier to work with first. Okay, so we'll try a couple here, okay? So for each of the following, determine the limit if it exists. If not, describe the discontinuity. So these are rational functions. They're made up of fractions. So the first thing I want to try is let's see if it comes out to a point. Let's figure out, we'll do it, the top part, and we'll do the bottom part separately. And because the top part is a polynomial, and the bottom part is a polynomial, a different polynomial, we can go back to our polynomial ideas. Let's move these down for a second here. In that, I can figure out the top one at 3, and call the bottom one G, the bottom one at 3. So what's that going to give us? It's going to give us 2 times 3 plus 5 on the top, and 3 minus 1 on the bottom, which means this limit is 11 over 2. So for this rational function, yes, it has asymptotes. Okay, there's an x on the bottom, but as I approach 3, we actually approach 11 over 2. There's a specific point on that graph. Okay, so I hope that makes sense in terms of we can do the top and bottom separately. I'm not going to show all this every time. I'm just going to do that, okay? So try the next one. What happens as we approach 4? Well, that's the same thing as we're doing f at 4 over g at 4. So I got 4 squared plus 1 over 2 times 4 minus 8. What do I get? I got 17 over 0. Oh, I got a 0. What does that mean? The fact there's a 0 on the bottom tells me there's a vertical asymptote at x equals 4. And I know that because I got a 0 on the bottom. I know it's at 4 because that's what we were approaching. Okay, that's really quick. There's a discontinuity in this graph. There's a break in the graph. Try the next one. Let's move these down a little bit here. Okay, let's see what happens as we approach -8. So f at -8 over g at -8. -8 plus 8. 2 times -8 minus 1. What do we get? We got 0 over -17. Okay, that comes up to 0. Can it come up to 0? Sure it can. We're approaching 0. That is totally different than the previous one. Previous one had a 0 on the bottom. That's an asymptote. 0 on the top, totally fine. It's a point. The point 0. Okay, we'll try D. Okay. I'm going to stop writing out the F at 3 and the G at 3. We're just going to do it now. We know what's going to happen here. 3 squared minus 2 times 3 minus 3 over 3 minus 3. What's that going to give us? On the top, we can get 9 minus 6 minus 3. Oh, it's 0. Oh, 0 over 0. Well, that's different. What does that mean? That means there's a hole at 3. I know that because I got a 0 over 0. Now the question was find the limits. Limits still exist for holes. So as soon as I recognize that it's a hole, I have to still figure out the limit. I don't do it for vertical asymptotes, but holes I do. To do it for a hole, we're going to have to go back and fix the function. We're going to have to change this function. So our function, right down here, f at x is x squared minus 2x minus 3 over x minus 3. This function can be simplified. Somehow, some way we can simplify it. And we know from rational functions we should often be able to factor them. So if we factor the top, x minus 3 and x plus 1, and the bottom stays the same, we notice that we can cancel out this. So this function is actually the same as x plus 1. So if I want to know the limit, as I approach, we're doing 3, I found there was a hole, we can still do it. We can do the limit now of x plus 1 as we approach 3. And we'll get 3 plus 1, or in other words, 4. So previously we said there was a hole because it was 0 over 0. We could fix the function, figure out where the hole actually is. We can now say there's a hole at x was 3, and it turns out that the y value is 4. Okay, so when you come across holes, 0 over 0s, you have to do a bit more work. You have to actually simplify to figure out that limit. Okay, let's try one more. The limit of this thing. Okay, we'll do what we've always done. 7 minus 0 and 7 plus 0. We're trying to find shortcuts here. What do we get? We get on top root 7 minus root 7 over 0. Oh, that gives me a 0 over 0. What does that tell me? It's a hole again. It's an indeterminate answer. Something weird going on here. Which means I can calculate the limit. I just can't calculate in the format that it's in. So I need to fix this. When we come across radicals, the way we fix them is we rationalize. And the way you rationalize is you take the radicals you want to get rid of and multiply by the same thing and the opposite signs. So I'm going to keep the 7 minus x, but I'm going to put a plus sign in between now. Right? And whenever I do the top, I got to do the bottom because I can't just magically make this question change. Okay, so this is rationalizing. Okay, so we're creating a new function. So we'll call this f of x now. What are we going to get on top? We'll get, well, think about FOIL here, okay? So we're going to do this times this. The root times itself cancels the root out. We've seen that before. When we do the outside part, this times this, and this times this, those two things end up with the Same terms, but opposite signs, so they cancel out. And then when we do the last piece, we're going to end up with a negative and 7 plus x. On the bottom, we have our x times root 7 minus x plus root 7 plus x. Okay, so we can simplify this a little bit. On the top, 7 minus x minus 7 minus x. On the bottom, x and root 7 minus x plus 7 plus x. Okay, this one is not so much fun to simplify. Keep going. On the top, 7 minus 7 is gone. We get negative 2x and x bracket root 7 minus x plus 7 plus x. We can now cancel something because it's multiplying on the top and the bottom, and I see an x here and an x here. So a simpler version for this function is negative 2 over root 7 minus x plus root 7 plus x. Remember, we did this so we can actually calculate the limit. The limit as we approached 0. That was what the original question was. So let's try it now. What happens as we approach 0? Well, on the top, we get negative 2. On the bottom, we get 7 minus 0 plus 7 plus 0. So we get negative 2 over root 7 plus root 7, which if we simplify a little bit more, it gives us 2 root 7s. And we can cancel those 2's. Same thing top and bottom. We get negative 1 over root 7. In other words, we've now proven there's a hole. We got that from the 0 over 0 at 0 and negative 1 over root 7. Now, that was painful. It wasn't hard, but there's lots and lots of steps to go through to rationalize something. So, a bit of a shortcut for us. It turns out that for things that involve holes, we can use a shortcut. We call it L'Hopital's rule. So if a function produces an indeterminate limit, 0 over 0, a hole, it can be shown that you can find that limit by taking the derivative of the top, the derivative of the bottom, and then doing the limit. It's a bit of a shortcut. If you go back for a second, go back to the easy one. Let's go look at f for a second. F had an indeterminate limit, right? 0 over 0 right here. Well, if we had taken the derivative of the top, which would be 2x minus 2, and the derivative of the bottom, which is just 1, and we found the limit of that thing, we would get 2 times 3 minus 2 over 1. Or in other words, 4. Right? 6 minus 2 over 1. Well, that's the exact same thing we got after we did our simplifying. That's way faster than having to go through and either factoring or rationalizing when you get messy things. So if we come across something that has an indeterminate, a 0 over 0, take the derivative of the top and the bottom, and then do your limit. It'll be much faster. Okay, so look at this first one here. We want to evaluate the limit. Let's try it the way it is. 3 squared minus 9, 3 minus 3. What does that give us? 0 over 0. Oh, there's a hole. Well, rather than trying to factor, and I could, there's nothing wrong with factoring. If you like factoring, do factoring. But rather than doing that, why don't we do the limit of x approaching 3 of the derivative? Derivative of the top is 2x, derivative of the bottom is 1. Let's see what happens now. 2 times 3, 6. That was much faster. What have I proven? I've proven there's a hole, because I got 0 over 0, at 3 and 6. Yeah, I think that's pretty quick, especially if you get to messy ones, which we'll get to in a second. Anyway, try the next one. Let's see what happens as we approach 5, the limit. We get 5 squared minus 8 times 5 plus 15, and 2 times 5 minus 10. So on the top, we get 40 minus 40, which is 0. On the bottom, we get 10 minus 10, which is 0. Oh, we got ourselves a hole. So instead of doing that, let's see what happens as we approach 5 for the derivative. 2x minus 8 and 2. Well, that's going to give me 2 times 5 minus 8 over 2, or in other words, 2 over 2, which is 1. there's a hole at 5 and 1. Now, I don't need you to write me down the whole part every time. The question just says evaluate the limit. That's what we've done here. The limit as we approach 5 is 1. Okay, try the last one. The messy one, the one with the root signs in it. Okay, let's try the basic one first, because if the basic one works, we don't have to do anything messy. All right, 4 squared minus 4 times 4. All right, so we'll get 2 minus 2 on top, which is 0, and 16 minus 16 on bottom, which is 0. Now this one would be pretty messy to work with, because it's got radicals in it, and there's some factoring you could do on the bottom, so we want to try to avoid that. Let's try taking the limit of the derivative. So as x approaches 4, the derivative of x to the half, because that's really what that means, right? Would be, oops, not equal sign, sorry, fraction. 1/2 x to the negative 1/2. On the bottom, we'll get 2x minus 4. Now let's see what happens as we approach 4. And we're going to get 1/2 times 4 to the negative 1/2 over 2 times 4 minus 4. Okay, what does this really mean? Well, this means, and you can try your calculator if you want to, there's nothing wrong with that. Okay, 4 to the negative 1/2 actually means 1 over 4 to the half, right? We're going to multiply here on the top now. And on the bottom, we'll get 8 minus 4, which is just 4. Okay, so on the top, we get 1/2 times 4 to the half. That's a root, right? Square root of 4. 1/2 times 1/2 over 4. In other words, 1/4 over 4. 1/4 divided by 4 makes 1/16. Okay, so that one is a little bit messier, but by doing the derivative idea, by using L'Hopital's rule, we can simplify the function to find the derivative first, rather than having to go through and rationalize or factor. A bit of a shortcut. Okay, that's the end of the lesson. I'm going to try some of the questions there, see if you can do them. If you're stuck, come see me and we'll figure it out.